The goal of this talk is to give you some background on recent advances in the last few years, thinking through stellarator coil optimization. I'm going to sort of focus on different ways to think through the problem, give some sort of survey on the different ways we think about this problem. But before that, I just want to thank my collaborators there's a lot of different collaborators on the work I'm going to show here. Special thanks to Matt. I'm going to reuse some of the intro coil slides he's used before. And thanks for the invitation to give this talk. So as I said, I'm going to give some background. I'm going to give a survey of different ways we can think about coil optimization. I'm going to then blaze through a whole big list of different things that have happened over the last year or two in coil optimization. This includes thinking through minimizing different types of strains on HTS tape, minimizing coils to obtain tolerable forces and torques at reactor scale. This actually turns out to be extremely challenging for a lot of stellarator coils. Trying to actually find the best coils possible by doing these large coil scans. And you have to typically do this plasma by plasma because different coils are going to look very different for different plasmas. And then I'm going to sort of compare and contrast some of the different ways we think about coil optimization, including the winding surface and filamentary methods, talk about some of my work in permanent magnet optimization and algorithms for that, and then talk about how we can hopefully scale this up to reactor scale, thinking through what are called dipole arrays, and this sort of funner idea where you take away all the power supplies and just rely on passive coil arrays. I sort of have some work showing if that's plausible at reactor scale. And then lastly, some methods for coil optimization that are very different and really think about the problem very differently than the winding surface or filamentary methods. And then I'll just conclude with sort of future needs for the community on this problem. Okay, so I'm going to go through this relatively fast. Most of you are stellarator experts here. Why do we need sophisticated coil optimization? Well, we have these complicated 3D plasma shapes. They require complex three-dimensional magnetic fields. And we want to generate those fields without requiring really large plasma currents. So we need three-dimensional complicated coils in general. In principle, this is a full free boundary problem. You're given some degrees of freedom of the coils. This can be the shape, location, currents of the coils. And you want to use those degrees of freedom to find a toroidal boundary where Bn equals 0 and minimize some physical properties of the corresponding MHD equilibrium corresponding to that boundary condition. Of course, this is the full free boundary problem, and this traditionally has been really hard to solve, not very robust when you try and do this in 3D. So we've tried to split the optimization problems into the jargon stage 1 and stage 2. Stage 1 is you just think about the plasma boundary. You change the shape of the boundary, and you try and figure out sort of what's an optimal boundary shape that gives you a good equilibrium that's going to make a good fusion reactor in practice. Stage 2 is given that plasma, so assume we already have a good stage 1 optimized plasma, can we actually create coils for that in practice? So the question is how to build coils such that ideally beta n is 0 on the whole prescribed plasma boundary. In practice, you can't make it perfectly 0 numerically. So instead, we minimize this FB metric, which is sort of a surface averaged B normal errors over the plasma surface. And clearly, if you get this thing to 0, you've satisfied your constraint that beta n is 0 on the plasma surface. Okay. The way we're going to do this is we have some degrees of freedom with respect to the coils, and we're going to choose those degrees of freedom to target this objective. We're soon going to add many other terms to the optimization problem, but this is requirement number 1 for coil optimization. Importantly, I do want to point out this is like a wider class of problems called inverse magnetostatics. You're given a B field on some surface or volume, and you want to find current sources to produce the field. And you can have lots of degrees of freedom, and in fact, lots of different ways to produce magnetic fields. So here I've shown there's a wide array of different types of coils you might consider for this, including these modular coils, which interlink with the plasma a single time, typically. These helical coils, which helically wind around the plasma and can interlink multiple times. And then these saddle dipole coils, which have no topological interlink with the plasma, okay? And if you're at reactor scale, these dipole coils are roughly equivalent to putting permanent magnets. These permanent magnets roughly produce dipolar fields. Okay, many of you know this, but this is an ill-posed problem if you don't add what we're going to call regularization. So if you look at the top solution and the bottom solution, they give you essentially the same magnetic field. That's because I can always take a little part of wire outwards and then back here, and those magnetic field contributions are essentially equal and opposite. So in total, these coil sets are giving you essentially the same error on the plasma surface. But obviously, we don't want to build this because this is a complete waste of time and energy and space. So we need some regularization to prevent this. This seems like a bad thing, but actually it's a good thing. There's a lot of freedom in coil design. We're going to add some additional terms to the optimization to basically say we don't just want a coil set which matches beta n is 0 on the plasma surface. We're going to ask that our coils do a lot more. They satisfy some good engineering properties. And we can ask for this because actually there's a sort of infinite class of coil solutions that give us roughly the same B field on the plasma surface. And we can use that extra degrees of freedom to ask for some engineering constraints on the coils. Okay, and the sort of traditional method has been this current potential winding surface method. The main benefit here, it's sort of simple theoretically and it's fast to compute and it's convex. It's a convex optimization problem. The idea is we're going to set up, so we have our prescribed plasma here in red. We're going to just imagine there's some toroidal surface in green that surrounds it. And we're going to say there's some sheet current that continuously is defined on this toroidal surface. And then we're going to set up this problem. And what's nice about it is you can write the sheet current in terms of current potential. This FB metric, which is trying to get the beta n errors to 0 on the plasma surface, it turns into a linear least squares problem. And then to avoid these sort of unwanted solutions, we add some regularization on, in this case, penalizing solutions that have very large current densities on the surface, okay? Which is sort of a reasonable thing to ask for when you're finding these solutions. Okay, so the pros is it's linear least squares. That means it's a convex optimization problem. You can provably solve it to the global optimum. And there's only two parameters to vary, which is where do you put this toroidal surface in green, and how much regularization do you want to put in? Obviously, it's got some downsides. You're not giving as many degrees of freedom as you can. You're not letting the coils move in the sort of third dimension. They're constrained on a surface. And at the end of the day, you get some solution for this continuous current density, but then you have to chop it up into coils, and that's going to introduce some errors when you do this process. Okay, and just to visualize this trade-off in regularization, if you do a high amount of regularization, you're going to get sort of simple-looking contours of the current potential, but you're going to get large BN errors on the plasma surface, and vice versa. If you want really high accuracy on the plasma surface, you're going to get much more complicated current potential contours, and it's going to be the coils you get out of this are going to look much more complicated. Okay, and one of the reasons I highlight this is there has been some work on these winding surface methods. That includes this recent work from Frank on quad coil. The idea here is we would like to add some additional terms into the winding surface method, but all the terms you want to add, like penalizing curvature and forces and so on, these are quadratic in the current potential, meaning the problem becomes non-convex. However, if you still dominantly are minimizing the linear least squares part of it, this problem remains nearly convex, and you can actually apply some sophisticated optimization techniques. This is called shore relaxation, and still, in many cases, provably get to the global optimum of the problem, even though you're in this like formally non-convex situation. So here's two examples. So one of them is we have this normal FB metric, but then we penalize a proxy for the coil curvature on the winding surface. And then similarly, we have another one where we basically constrain it such that contours of the current potential can only give you poloidal contours. So this is sort of a topological constraint on what the contours look like. And just to show you what that looks like, we get a solution with quad coil. You can see visually that the current potential is only giving you poloidally connected contours. And if you try and do the same thing with traditional winding surface methods, you basically just have to scan this regularization parameter lambda until you manage to get a solution where the contours are poloidally closed. And anyways, this takes longer. You have to do the full scan. And actually, at the end of the day, you get a slightly worse solution in terms of solution accuracy. So I want to highlight this as sort of some of these next steps in winding surface methods and adding in some of the more some of the more complicated terms we want to regularize this problem with. Okay. So that was sort of briefly on winding surface methods. Let's talk about a more popular method these days, which is filament coil optimization. The idea here is this is going to better represent real coils. What you do is you represent them as infinitesimally thin three-dimensional curves in space, and you just parameterize them somehow, okay? So you can use splines. In this case, I've expanded the XYZ coordinates of each coil in a finite Fourier series. But of course, choose your representation that you like. The objective here is, as usual, match beta n on the plasma surface. And then we're going to talk about this very long list that of regularization terms we're going to start adding here. But sort of the structure of the problem is similar. The downside is this is going to be non-convex, actually really, really non-convex, as I'm going to try and convince you. That means there's lots of local minima. You might get stuck in some of these suboptimal local minima. This typically means you need good initial guesses, more sophisticated algorithms for optimization, and often, in fact, I think probably we should be using this Fourier continuation method, where if you have this finite Fourier series, you just start with a few Fourier modes parameterizing the curves. You converge that subproblem, and you use that as an initial guess on a new problem with more Fourier modes, and you proceed sort of iteratively adding more Fourier modes in a sequence of subproblems. And in fact, we do this all the time for stage 1 optimization, and I'm going to try and convince folks that maybe we should think about this for stage 2, and it is in fact sometimes used. Okay, to talk more about these different terms we want to add to this problem, one of the advantages or disadvantages of this approach is you can add lots and lots of sophisticated terms that give you regularization. So the first one, sorry, the notation change, but this is just match beta n on the plasma surface. And then we've added a bunch of other ones. So we want to penalize the pointwise forces along the coils, total arc length variation, penalize the total coil length, penalize the minimum coil-coil distances, penalize the coil plasma surface distance, and penalize the coil curvature. And this list is going to get even longer somehow in a few slides. But this is actually sort of typically what folks are doing these days for coil optimization. So that's nice. We can put in a lot of engineering properties that we want to minimize. There are sort of two frustrating things about it, which is most of these terms are quite nonlinear in the degrees of freedom. So this thing is like horribly non-convex. And moreover, all of them you have to weight somehow. You have to decide what the relative weights of all these terms should be in the optimization. And that requires some fiddling or some extra optimization to decide the relative importance of all these terms. Okay, so what if you just plot what the optimization landscape looks like? And here I've taken the Landrum and Paul QA stellarator. I've initialized 4 circular coils per half field period. And I've just given it a single Fourier mode in this finite Fourier series expansion. And now I'm just plotting what the landscape looks like as a function of the cosine mode of x and y. Okay, so I've basically just taken like a 2D slice through the optimization landscape for one of these sort of typical filament optimizations. And what you see is it's got this pretty crazy looking spectral structure. I'll mention, by the way, the color bar is log of the objective value. So there's order of magnitude differences in the quality all over this landscape. Before people start throwing things at me, the horizontal lines and the vertical lines, I have not been careful. I just scanned the values of these. these sort of blow-up lines are basically where you get unphysical solutions. The coils become self-intersecting, or they intersect with other coils, or they intersect with the plasma surface. And at those points where you get sort of like unphysical things going on, you get blow-up in the objective value. So yeah, these horizontal lines, basically it's telling you you've done something not very smart. And again, this is not an optimization. I'm just basically trying to visualize a 2D landscape here, okay? But I do want to point out, even if you ignore these sort of blow-up spots, there's still sort of a rich structure underneath in the landscape, okay? And obviously, this is this is actually a sort of easier case. Usually, we use many more Fourier modes than one. So I expect this landscape to get much more complicated, actually, in practice. Okay, with that, I now want to rattle through some of the recent work in filament optimization. This was already discussed by Paul at the Princeton meeting. I'll just mention again, one of the important things for HTS is that you can have different strains and you want to reduce them during optimization. One is this normal direction of the tape, one is binormal, and then one is torsion as you twist the tape. And what they were able to show is they could build this into optimization. In the case of CSX, they actually added a little bit of torsional strain, a little bit of twist, and in doing so, were able to get their binormal strain below this 20% level. Paul can correct me, but my impression is this binormal strain is sort of the most dangerous one. So I think the target here was to get this binormal strain to some reasonable values. And they were able to do so with a little bit of twist in the tape. Some work that's been pushed forward by Senna Hurwitz and Matt Landryman is looking at coil-coil forces. And in particular, they have a sequence of papers on computing self-forces and self-inductances in circular or rectangular cross-section wires. So I told you all the filaments are infinitely thin. But for the purposes of calculating self-forces, we're free to imagine that they have some finite cross-section. So I've plotted a rectangular cross-section wire here, given you the sort of fast formula that was derived for the self-inductance. And then we put some of this stuff into optimization. You're able to basically show that you could reduce the point-wise forces on the coils. Typically with these, the point-wise forces are most extreme on the inboard side where the coils are closest together. And by directly targeting the forces, you can reduce them at least by some moderate amount, maybe a factor of 2 or something like that. But still, because these reactor scale stellarators, as I'm going to show you in a moment, actually are on the bounds of what is within the material tolerances for forces, a factor of 2 might be very worthwhile. Okay, a few other things I want to highlight from some of the work we've been doing with forces and actually torques is that another thing that was done was these large scans to try and navigate the landscape of possible coil solutions and find optimal ones. And basically, Sienna and Matt did this thousands of runs with slight hyperparameter perturbations. In other words, they slightly re-weighted those weights on each of the terms in the objective, and generated a big plot like this, where you can really easily see some of the important correlations. So I'll just point out the x-axis here is the BN over B errors. So this is like the normalized field errors on the plasma surface. In other words, you want to be on the sort of left side of this. So these are the very accurate solutions. And then on the y-axis, we have the maximum forces. And on the color bar, we have coil surface distance. And these sorts of plots can basically show that there's a strong correlation between the maximum forces and the coil surface distance. And this sort of confirms our intuition. As you ask that the coil surface distance is larger, the coils on the inboard side have no choice but to get closer together, and then invariably the forces have to get larger. So these sorts of scans let you see these correlations in the data. And there's a whole host of these in Sienna's paper and my paper I'm going to talk about on dipole arrays. So please take a look at that if you're interested in some of these correlational studies. I'll mention also there's a huge database of coil solutions in Quasar from Andrew. And I think these sorts of things could be really valuable to generate and look at in the community. One of the really interesting things we found in the process is it appears that you can, if you're thinking about torques on the coil, in particular, we're thinking about the torque measured from the center of the coil, so like the propensity of the coil to want to rotate about its center. You can roughly reduce it to 0 with without substantial accuracy loss. So I'm showing the BN errors with one color bar over here, another one over there. And what you see is you get something like 4 times worse errors, but the net torques actually you can reduce by like 4 or 5 orders of magnitude if you put it into optimization. Something we were a little worried about is maybe there are some trade-offs of doing this. In fact, these coils maybe look a little more like they have slightly higher curvature or something like that. So again, we performed one of these like high-dimensional scans of different coil solutions and asked, are there big trade-offs when you target the net torques on the coils? And as far as we can tell, the answer is no. So I'm plotting another one of these correlational plots. Against the color bar here is now max curvature. And the point of this plot is it's basically just a jumble of dots. There's not a clear correlation with the net torques and the maximum curvature. And in fact, importantly, this y-axis is on a log plot. And there are solutions up here that are accurate that have 500 meganewton meters of net torque about the coil center. And there are perfectly other ones that are just as accurate that have 1/1,000,000th the net torque. So this might be something for experimentalists to think about. You can basically turn off the net torque by directly targeting it in optimization. Okay, I think this is the last thing I want to point out from this paper. Another useful thing is because we've generated this big scan, we can actually compare it to existing solutions in the literature. This coil set is from this 2022 Wetschong et al. Solution, finding coils for the Landrum and Paul QA stellarator. And there's some text here, but the sort of short version is we find an equivalent coil set in these large scans, which, because we've targeted the forces, reduces the forces something like 30%, but otherwise gives you roughly the same coil solution. And actually, if you look at these coils like coil by coil, you can see they actually look very, very similar in the shapes that you're getting. So you're basically taking Florian's coils and slightly perturbing them to reduce the forces is enough to sort of get you a roughly 30% reduction. I'll mention also, look at the absolute force magnitudes here, which is like 0.3 or 0.4 meganewtons per meters. This is like approaching the tolerances, or maybe at the tolerances of even our best like industrial strength HTS coils. So getting even like 30% reductions in the point-wise forces can be very valuable when you're like on the threshold of feasibility. Okay, with that, I'm gonna sort of turn for a second towards these permanent magnet arrays, and then I'm gonna talk about dipole arrays. As many of you know, there's been some work on permanent magnet arrays. These only work at laboratory university scale, but this was successfully built, this Muse stellarator was successfully built at Princeton, and I think they got first plasma 1.5 to 2 years ago. And what's really nice is, at least at this scale, you can sort of 3D print these permanent magnet holders. You can get away, in this case, with just planar TF coils and generate all the three-dimensional magnetic field shaping you need to have a stellarator. In fact, Muse is quite a good stellarator, although it's very small. And the question is, so we can't use magnets at the reactor scale strengths. Question is, can we scale up some of these ideas to what are called dipole arrays, which is a similar thing, except for each of these is no longer a magnet. It's a little loop of superconducting wire, or it's a little superconducting coil. Yeah, the question is this feasible as you go to reactor scale? Before I get there, I do want to point out that some of the work myself and others have done over the last few years on permanent magnet optimization has really improved the quality of solutions you can get here. This solution actually was pushed forward most by Ken Hammond. I don't know if he's here. But basically, they had this 2022 paper, PM for Stell, where they were looking to design a permanent magnet array for NCSX scaled to a half Tesla on axis. And so this was only in 2022, and then 2 years later, after some algorithmic work from me and Ken and Matt and a few others, we were able to achieve essentially actually a slightly better solution than them. So here are the total FB errors. And we use about 10,000 fewer magnets, or close to 30% fewer magnets in the solution. When you're actually, that's for a half field period. So for the total thing, you actually use 60,000 less magnets in the solution we got, and you get a better error. So my point here is that if you take the time to do some more sophisticated optimization things, there can be big payoffs, both in the permanent magnet space and I think more generally in coil optimization. And that's something I'll touch on at the end about sort of future directions. Just to show you here, this is the radial component of the dipole moment of each of the permanent magnets in the original NCSX PM for Stell solution. And then this is our solution. And just to see, there's like wide swaths of magnets here at the top and sort of on the bottom here that we are able to get rid of in this new solution. Okay, so onwards towards reactor scale. So we were wondering, there's been some work on if dipole coil arrays can reduce the complexity of these modular coils. We wanted to basically see, can you actually scale this and make it feasible at true reactor scale and use it to reduce the complexity of the sort of main TF coils. You can't get rid of the main TF coils, of course. And actually, we sort of do the most maximalist thing possible, sort of best case scenario. We jointly optimize all the coils in the dipole array and the TF coils at the same time. And we actually let the dipoles to fully vary their currents, shapes, orientations, and locations. So they have like full degrees of freedom to do whatever they want. I will say, for the purposes of this work, we mostly constrain them to be like identical circular coils for geometric simplicity. But in practice, the optimization lets you give them full shape degrees of freedom as well. And okay, I mostly put up the optimization problem to scare the daylights out of you. There's now this FB term. There's terms related to regularizing the toroidal field coils. There's terms that couple the toroidal field coils and the dipole coils, like coil-coil forces and so on. So I've just listed a bunch of these. Okay, these are like pointwise forces and torques. Net forces, net torques, pointwise forces, pointwise torques, and the list goes on and on and on. And again, this is mostly to scare the audience. So, okay, so here's an example of a typical solution. So again, we let them float around and we let them change orientation. So in general, you don't get like some simple surface that they lie on. But what is useful is we're able to find some solutions like for this 2-field period compact QA stellarator from Schutt-Hannenberg. We use 16 dipole coils per half field period. They're all identical circular coils. They're all over 1.5 meters from the plasma surface, as you would need at reactor scale. Usefully, we're able to show that the TF coils the complexity is reduced, and the total coil length is reduced to about 75 meters. If you try and do the same thing without the dipole array, the coils get more complicated, and the total coil length goes up by about 20 meters. And importantly, the errors also go up. And what's kind of frustrating about this is the device is so compact that if you're like, okay, I want the errors to be lower, I'm going to add one more TF coil. So you try and do a 3-coil solution. You really don't do any better. And the reason is you just literally don't have enough room to put a 3rd TF coil in there without like getting the forces really, really large or otherwise like making them super curved in the middle. So yeah, this is sort of maybe a useful lesson that some plasmas are certainly more compatible with these kind of dipole arrays, or could use these dipole arrays more effectively, because, for instance, putting a third coil just like gives you nightmares. This is like, you might as well stick with 2 at this point. Something else to notice, we actually have to very directly target the forces and torques on the dipoles.